Hello class, welcome to this video. I promised I would go through a couple more problems working with the chain rule, and then I also want to get into section 3.5, which is about the trig functions, and within that we're also going to hit a couple of problems that involve the chain rule. So I picked out a couple of problems from the homework that I thought might have been a little bit of a challenge. First one is number 27. It says find the derivative of this function. And it looks to me like at first glance looking at this function, I see a square root function, I see a cube function, and I see a product of two other functions inside here. And I want to find the derivative of this a couple different ways. One way, maybe the most difficult way, is to look at this as there's really like three functions here. There's the square root function, there's the cube function, and then I'm going to call the stuff inside here the other function. So if we start on the outside, this is really the same thing as just saying x squared times 5x, or 5 to the x, raised to the third, and then raised to the 1/2 power. So if I start on the far outside, we're going to get that dw over dx, the derivative of w with respect to x, is going to be equal to, we'll bring down the 1/2, and then we've still got x squared times 5 to the x, raised to the third, raised to the negative 1/2. And then I see inside here we've got a function raised to the third power. So it's going to be times 3 times the function, x squared times e to the 5x, raised to the second power. And then we work on the inside again, and I see a product in here. And so the product rule says take the derivative of the first, 2x, multiply by the second, and then add to that the first function, x squared, and then times the derivative of 5 to the x is natural log of 5 times 5 to the x power. Okay, so that's one way that you could approach this problem. The next way is I'm going to just simplify the exponents a little bit and say, you know, if we raise a power to a power, we can also rewrite that function just as w is equal to x squared times 5 to the x raised to the 3/2 power. And then just, this is just a function raised to a power then. So dw over dx will be equal to 3/2 x squared times 5 to the x raised to the 1 less power would be the 1/2 power. And then times the derivative of what's inside, which again is going to be the product rule. So 2x, 5 to the x, plus x squared, natural log of 5, times 5 to the x power. Okay, so actually, you know, this part right here is what you're going to get if you simplify just this part here. It will simplify down to that part. Okay, and then let me show you one other way that we can do this. If I look at this rule, we can say that, or we could rewrite w again, that if this is a product, this 3/2 power can get applied to the two functions that are on the inside, and the rule is to multiply these powers together. So we're going to end up with x squared to the 3/2, that's going to give me x to the third power, and then if I multiply these out, we're going to get times 5 raised to the 3/2 x power. And then, if I take the derivative with respect to x, this is just going to be the product rule. So we're going to get 3x squared times 5 to the 3/2 x plus the first function, x to the third, and then times the derivative of this. Now this is 5 raised to a function. So my rule is take the natural log of the base times 5 raised to the function, and then we've got to multiply that by the derivative of the function, so we're going to multiply by 3/2. Alright, and if you simplify all this, you're going to get the same thing that we have up here and as well as up here. So there's really three different ways that you could do this, and you're going to get three different kinds of looking answers. Okay, so 27 was quite a bit involved with that one. The next one that I'd like to look at is number 32. And number 32 is a fraction inside of a radical. Alright, this one I don't think is quite as bad. This is going to be just x squared plus 9 divided by x plus 3. And then I think the easiest way to do this one is just raise this to the 1/2 power. Alright, so looking in here I see we've got a half power and then we've got a quotient in here. So the chain rule says take care of the outside function. That's going to be 1/2 x squared plus 9 raised to the x plus 3, and then decrease the power by 1, and then multiply that by the derivative of what's inside, and that's going to be an application of the quotient rule. So the derivative of the numerator is 2x times the denominator, x plus 3, minus the numerator, x squared plus 9, times the derivative of the denominator, which is 1, and then all of that divided by x plus 3 quantity squared. Okay, and I think that's probably the most straightforward way to do that problem. Okay, the next one. I'd like to do this one two different ways. Notice that this is a function of z, so z is the variable and a and b are just going to act as constants in this function. So the first way I'm going to do this is just leave the function the way it is and take the derivative of this with respect to z, and so we're going to end up with 4 times this function, b divided by a plus z squared to the third, and then I'm going to take the derivative of what's inside, and if I think of this as being a quotient, the derivative of the numerator, now remember this is a constant, so the derivative of b is just going to be equal to 0, and then times a plus z squared minus the numerator, b, times the derivative of the bottom. Now the a again is going to be a constant, the derivative of a is going to be 0, and the derivative of z squared is going to be 2z, and then all divided by a plus z squared squared. Okay, and then if you simplify this a little bit, let's see, this is going to end up dropping out, and you're just going to end up with 4 times this to the third power, and then you're going to end up with times a negative 2bz divided by a plus z squared squared. All right, again, I think that that's probably the easiest way to think about that one, but you could just as well rewrite the function as, let's see, it would be b times a plus z squared, and then all of that raised to the 4th power. Let's see, raise this to the negative 1 power, and then all that raised to the 4th power. So taking the derivative of that, the way it's written, we're going to get 4b a plus z squared to the negative 1 power raised to the 3rd power, and then the derivative of what's inside. Right, you can make life easier if you don't think about this as a product. This is just a constant times a function, and so the derivative of that's going to be just the constant times the derivative of this function, which will be negative 1 times a plus z squared to the negative 2 times the derivative of what's inside, which will be 2z. All right, and this will give you an equivalent answer to the one that we got up here. All right, so if you're not getting exactly the same answers as what you see in the back of the book, check to see if you got just a simplified version of the answer that they gave. Okay, another one I want to look at is number 37. Okay, 37, I think we did one similar to this probably in class, but I see this as a product, and then I see within the product we've got a kind of a messier function here that's going to require the chain rule. So the derivative of this, dw over dt, or just w prime of t, is the derivative of the first function, 2t plus 3, times the second function, 1 minus e to the negative 2t, plus the first function, t squared plus 3t, times the derivative of the second. Now the derivative of 1 is going to be 0, and then the derivative of this is going to be negative e to the negative 2t. That's the derivative of e to a power. And then we've got to multiply that by the derivative of the power, and the derivative of that's going to be just -2. Okay? All right, so product rule, and within the product rule there's a little bit of chain rule. Okay, that one I don't think is really too bad. Okay, then 45 is kind of a mess. We've got e raised to the e raised to the y squared. So I see one function is this e raised to a power. I see another function is this e raised to a power, and then the power is also a function, and it happens to be a function of y. So let's start out with this e to the power. The derivative of e to a power is e to the power. Okay, then times the derivative of the power. Now the power is this. The derivative of e to the y squared is e raised to the y squared. And then the derivative of that is going to be just 2y. Okay, so that's kind of a weird function. You're probably not going to run into a function like that other than something that's been made up here to make you think about the chain rule. Okay, so hopefully those clear up some of the questions you might have had about the chain rule and working with the chain rule, and we're going to run into that chain rule again when we start working with the trig function. So today I want to talk about the derivative of the sine function, the derivative of the cosine function, and the derivative of the tangent function. And I think we'll wait until I get back on Monday and we'll talk about the derivative of secant, cosecant, and cotangent. And I think we can probably derive those from the ones that we derived today. Okay, so first thing I want to look at here is I want to fill in on your derivative sheet the derivative with respect to x of the sine of x. All right, and what I'd like to do is start with thinking about what the derivative of this function might look like. Okay, and so I'm going to switch over here to GeoGebra, and I've got that program that I've written that will sketch the derivative of this function. Now I want to take a look at sketching the derivative of this, but I want to think about what are some points that are going to be on the graph first. So if I look at that point right there, I've got a couple of traces turned on here that I don't want on. Let's turn that trace off, and that trace is already off, it looks like. No, it's not. Let's trace off. Okay, so if I move the cursor to here, it looks like the derivative at about that point is equal to 0. So let me move a point to where that derivative is equal to 0. I'll call that point D. And then if I keep moving across here, it looks like when we get to about that point, I'd say the slope of that red line looks to be about 1. All right, so let's put a point there at 1, right about there. And then if I keep moving across, when I get up to the top of this peak, it looks like the derivative right about there is equal to 0. So let's put a point there. And then keep moving. By the time we get over to here, the slope looks to be about -1. So let's put a point down here at -1. And then we'll keep moving till we get down to there, and that looks like the slope is about 0 again. So we'll put a point there. And we'll just keep moving along here. It looks like the derivative there is about 1. So we'll put a point at 1 and keep moving. It looks like 0 there, about -1 there, 0 there, and so on. All right, so I'm just going to put these in kind of quickly. At the peak here, the derivative is equal to 0. Where this crosses the x-axis, it looks like the slope there is about -1. And then over here at this valley, the slope looks to be about 0 again. And then here, the slope looks to be about 1. All right, then back down to 0 again, about there, and then -1, and then back up to 0 again. All right, so there's some points that look like they fall on the derivative of this function. And if you think about what that looks like, it looks like this pattern just kind of repeats over and over and over. And it looks like, where the derivative is positive, the function's increasing. Where the derivative is negative, the function's decreasing. But I think that the points that I plotted here really kind of follow another kind of a sinusoid function. the one that I think we might recognize. All right, so let me put the trace on and see how close we came with all those points. All right, so we'll trace this point and move across here, and we get a nice curve that looks like that just kind of oscillates back and forth. Okay, and I think that you might be able to recognize that function as being just the cosine function. All right, so let's see if that looks like the cosine function. If I just type in here f of x equals cosine of x and graph it, okay, you can see that that graph is the black graph, and it goes through all those dots that you see there. Okay, it looks to me like that's pretty convincing that, the derivative of that's going to be cosine. All right, but what I'd like to do is go through a bit of a proof of why this works out the way that it does. All right, but it looks like the derivative of sine is just equal to cosine of x. Okay, so let's look at the proof of this. Okay, we'll prove one of these, and then I think the rest of them we'll just take we'll just do a graphical approach. All right, so the proof, there's a couple of things that we need to know. One is we need to know, or we need to recall, that if you go back to what you did in pre-calc or in a trig class, you had a formula that said sine of, I think books probably used alpha and beta, and this is one that you probably recall that there were a bunch of formulas like this, but maybe you don't remember exactly what this one was. The formula for this was the cosine of the first angle times the sine of the second angle plus the the sine of the first angle times the cosine of the second angle. All right, and there's probably one section in your trig proofs where you had to remember that one. Then there's also a couple of limits that I want to look at. The limit as h approaches 0 of sine of h divided by h. We're going to need to know what that is. And I also want to look at the limit as h approaches 0 of cosine of h minus 1 divided by h. I want to know what that limit is as well. Okay, so to talk about those limits, I want to use my calculator just to convince myself what these two limits are going to be equal to. So first I want to make sure that my calculator is in radian mode, and I want to look at what happens if I take the sine. What happens if I take the sine of some really small number and divide it by that same small number? Okay, so that it's 0.99999. All right, to me that looks like that limit is going to be pretty close to 1. All right, so let's say that we'll accept that limit's equal to 1. Then I also want to look at this limit. What happens to cosine of h minus 1 divided by h? So let's start out with a right or left parenthesis. Cosine of a small number minus 1. And then that whole thing divided by that same small number. Right, we end up with negative 4.999 times 10 to the negative 4th power. This is a really small number. Okay, it happens to be a really small negative number, but it's pretty close to 0. All right, so let's say that that is going to be equal to 0. Okay, which we'll see later on that there's a way that we can actually show that algebraically that it is equal to 0. All right, so we need this, and we need this in order to prove that that's true. All right, so we'll go back to the derivative with respect to x of the sine function. When we go back to the definition of the derivative, this will be the limit as h approaches 0 of this function, sine, evaluated at x plus h, minus the function sine of x, all divided by h. All right, so we get limit as h approaches 0. All right, the reason we need this formula up here is because we're going to use that here to expand it, and we're going to write that as cosine of x times sine of h plus sine of x times cosine of h minus sine of x, and then all that divided by h. Okay, so all I've done is I've replaced this sine of x plus h with the expansion up here. Okay, the next thing I want to look at is rewriting this slightly differently. So we'll get the limit as h approaches 0. I'm going to write this as cosine of x sine of h. And then over here I notice that there's a sine function in common, so I'm going to factor that sine of x out, and we'll be left with cosine of h minus 1. And then all this is going to be divided by h, so I'm just going to write this as divided by h and divided by h. Alright, then if you notice what happens here, sine of h divided by h, we said that that was equal to 1. So this part of the function just ends up becoming cosine of x times 1. And then as h goes to 0, this part over here is going to go to 0, and then 0 times anything is just going to be equal to 0, and we're going to be left with cosine of x. Okay, so on your derivative sheet, you might want to write this one in, that the derivative of the sine function is equal to cosine. Alright, so what I'd like to do next is just work through a couple of problems with finding the derivatives. Okay, so suppose we have a function like f of x is equal to, let's say, x squared plus sine of x. And the question is to find the derivative. Okay, so we've got a rule for this one. The derivative of x squared is 2x. We've got the sum of two functions, so our rule says to just add their derivatives. The derivative of sine is cosine of x. Okay, so that one's a pretty straightforward one. Second example. Suppose f of x is equal to, let's say, x to the third times the sine of x. All right, and the question is to find the derivative. Okay, so I see a product up here, so we're going to apply the product rule. Product rule says take the derivative of the first, 3x squared, times the second, sine of x, plus the first, times the derivative of the second, and the derivative is, derivative of sine is cosine. Alright, so just product rule. Another function we're going to plug in there is the derivative of sine is equal to cosine, not sine. Okay, next one. How about f of x is equal to x times sine of x? All right, this one's actually a little bit easier than the one we just did, but this is a function that I had at least one of you come up to the board and sketch the derivative, and we're going to see how close we got with our sketch. So the derivative here is going to be f prime of x is the derivative of x is 1 times sine x plus first function x times the derivative of sine, which is cosine of x. All right, now I'm going to go back to GeoGebra and sketch the graph of x times sine x. All right, so let's see, let's get rid of that. And our function, f of x, we're going to change this to x times sine x. Sketch the graph, and get rid of that trace. And let's just ignore all those points that are on there. All right, and remember that when we did this before, I had somebody come up to the board and we came up with the derivative of this function. And let's see if that trace is still turned on. Yeah, it looks like it is. All right, so when we did that, we ended up with a derivative that was, kind of messy. It was something that looked like this. And again, we were just looking at where is the function increasing and decreasing and where is it equal to 0. All right, so if you connect all those dots, you should come up with a function that is the derivative of the blue graph. All right, now we just said that the derivative of this function is really 1 times sine x plus x times cosine of x. All right, and when I graph that, Right? You can see that that graph goes through all of those dots that you see on there. Right? So this was a function that's really kind of messy looking, but we just figured out how to do this algebraically and find the derivative of that function that way. Okay? All right. Let's take a look at another one. Suppose that our function is, now your book is going to write these this way, sine to the fourth x, right? I don't really like writing them that way. I'd rather write this as sine of x and the whole thing raised to the fourth power, but that's what that means. All right, so if we take the derivative, this is a function raised to a power, and this is an application of the chain rule. Right, the chain rule says take the 4 down, multiply by sine, raise that to the third, and then multiply by the derivative of what's inside, which is the cosine of x. Okay, so chain rule. Another application of the chain rule would be something like f of x is equal to sine of, let's say, 3x plus 1. Right, so I see chain rule here. I see this function plugged inside of the sine function. And our rule is to take the derivative of the outside function first. The derivative of the outside function is going to be the cosine. Remember, leave the inside function alone. And then multiply by the derivative of the inside function, which in this case is just going to be equal to 3. Okay? One more involving the chain rule. F of x is equal to e raised to the sine of x. We're going to find the derivative of that. Okay, so this function again is going to be a composition of the exponential function, and then this sine function is plugged into the exponential. So we'll take care of the exponential function first. The derivative of e raised to a power is e raised to the power, and then times the derivative of the inside function, which is the cosine of x. Okay, so these problems that are over on this side, those are all applications of using the chain rule in different ways that involve the sine function. Okay, let's try a couple more. What about if f of x is equal to sine of x squared times e to the x power? And we want to find the derivative. All right, so again, I see a couple of different functions in here. I see the sine function, and then I see this function inside, which happens to be a product. So if I think of the sine function as the outside function, this is the function that's plugged into it. We're going to take the derivative of the outside first, is cosine. Leave the inside function alone for now. And then we take the derivative of the inside, which is going to be an application of the product rule. The derivative of x squared is 2x times e to the x plus x squared times the derivative of e to the x, which is just e to the x. Okay, so again, chain rule with product rule kind of tucked inside. All right, one more of these. Let's look at f of x is sine to the fourth of x squared plus 3x plus 1. All right, which again, it's the same thing as writing sine of x squared plus 3x plus 1 all raised to the fourth power. Okay, so this is a composition of functions, but there's actually a function here, and there's a function here, and there's a function here. I would say that raising to the fourth power is the furthest outside function, so we'll take care of it first. So 4 times sine of x squared plus 3x plus 1 raised to the third power. And then we're going to take the derivative of the inside here, and the derivative of the inside is, again, a composition of functions. I'm going to take the derivative of sine as cosine of x squared plus 3x plus 1. And then I got one more step, and that is to take the derivative of this quadratic, which is just 2x plus 3. All right, so chain rule involving the sine function. This is kind of a messy one. It's got 3 different functions in there, and those typically end up being a little bit more of a challenge. Okay, so that's working with the derivative of sine. Now, the next thing I want to do is move on to finding the derivative with respect to x of cosine of x. Right, and this one, the proof of this is very similar to the other one, and so I'm not going to go through all the proof of this one. I just wanted to give you some convincing evidence what the derivative of this function might look like. So if we go back to GeoGebra, and let's clean up the mess that we have here. Let's go move this over here. We'll get rid of that graph. We'll get rid of the derivative of that function. And let's change this function to cosine of x. Okay, so there's the cosine function, and really all I want to do is find out what's the derivative of this function. All right, so I've got the trace already turned on. Let's just see what kind of a graph we get when we do this. All right, again, I don't think you should be surprised that we're going to get another sinusoidal graph because the function is periodic. We'd expect that the derivative is also going to be periodic. Okay, and if you look at that function, that looks like maybe a familiar function that we know. In the past, students have said, well, if the derivative of sine is cosine, that maybe the derivative of this is sine. But if you graph the sine function isn't quite that graph. Okay, we've got to take that sine function and actually flip it upside down, and the derivative of sine, or the derivative of cosine, I'm sorry, is actually the negative sine function. Okay, this is a function that's the sine function but flipped upside down. Okay, so again, I could go through the proof of that one, but I think really we would just want to cut to the chase on this one and say the derivative of cosine is negative sine. Right, and it's important that we keep track of this negative sign. It's going to cause us a little bit of trouble later on in the course. We've got to make sure that we keep track of where the negative sign is. Okay, so the derivative of cosine is negative sine. This is a function that tells me how this function is increasing or decreasing. So what if we've got f of x is equal to, let's say, 3x times cosine of x, and we want to find the derivative. Okay, I'm going to think of this as a product rule. Product rule says take the derivative of the first, that's 3, times the second, cosine, plus the first, and then times the derivative of the second, and the derivative of cosine is negative sine. Okay? Alright, so there's one example. Another example, suppose that our function is sine x times cosine of x, and we want to find the derivative of this function. All right, and so again, this is a product, so take the derivative of the first, the derivative of sine is cosine, times the second, plus the first, times the derivative of the second, which is negative sine. So you could write this as cosine squared x minus sine squared x. Okay, that's the derivative of sine times cosine. Okay, next one. Suppose we've got f of x is cosine of x to the third plus 3x plus 1. Find the derivative. Alright, so chain rule. Chain rule says take the derivative of the outside function, negative sine, of x to the third plus 3x plus 1, times the derivative of what's inside is 3x squared plus 3. Another application of the chain rule. Okay, next problem. Let's look at f of x is, well, let's make this one a little bit tougher, e to the square root of cosine of x. Okay, so finding the derivative of this one, we've got an exponential function, we've got a cosine function, we've got a square root function. The furthest outside function is the exponential. So this is going to be e raised to the square root of cosine of x. Right, we can think of this as e raised to the cosine of x to the 1/2 power. So taking the derivative of this is going to be 1/2 cosine of x to the negative 1/2 times the derivative of this is negative sine. Okay, so sine and cosine, derivative of sine is cosine, the derivative of cosine is negative sine. One more that I want to look at is, what about if our function f of x is sine of x divided by cosine of x? All right, and you might recognize this as, from a trig identity, this is the tangent of x. So we're going to derive the formula for the derivative of tangent here. All right, so if tangent is defined as sine divided by cosine, then to find the derivative of that, I can use the quotient rule. Quotient rule says, take the derivative of the numerator. The derivative of sine is cosine of x times the denominator is cosine of x again, and then minus the numerator, sine of x, times the derivative of the denominator is negative sine of x, and then all of that divided by cosine of x quantity squared. All right, and then this one I am going to simplify a little bit. This is the same thing as cosine squared x, and then I've got a negative times the negative is going to give me positive sine squared x, all divided by cosine of x squared. All right, and of all the identities we should remember from trig, it should be sine squared plus cosine squared is 1 divided by cosine squared x. And then one other thing we should probably remember is that the reciprocal of cosine is secant. All right, so the derivative of tangent is secant squared. All right, so it's another one that you should probably add to your list. The derivative with respect to x of tangent of x is secant squared x. All right, so let me go through just a couple of examples using the tangent. These are all formulas I'm going to expect that you have memorized. So let's say that we've got a function f of x is x to the 5th power times the tangent of x. Find the derivative. Right. All right, so we should be thinking product rule. Derivative of x to the 5th, 5x to the 4th, times the second function, plus x to the 5th, times the derivative of the second, which is secant squared. All right, one other one. F of x is tangent of x squared plus 1. Find f prime. Okay, this is a chain rule again, so derivative of the outside function will be secant squared. Leave the inside function alone, x squared plus 1, times the derivative of the inside function, 2x. Okay, very last one. F of x is e raised to the tangent of x. F prime. Derivative of e to a power is e to the power. Chain rule says times the derivative of the inside function, so this is going to be times secant squared x. Okay, so that should give you, three more functions that we're going to be working with is the derivative of sine, the derivative of cosine, and the derivative of tangent. On Monday we'll talk about the derivative of the other three trig functions. You can derive those using the functions that we have so far. One last application problem is, suppose that we're looking at the level of the water off a pier, and over time the tide is going to kind of come in and go out, and let's say that the depth of the water, d of t, is equal to, let's say, 15 plus 3 times the sine of pi over 12 times t, and here t is number of hours after midnight. Okay, and what I want to know is how deep is the water at, let's say, 5 a.m. And the other question is the water rising or falling at 5 a.m.? Okay, so the first question is really pretty easy. All we got to do is take 5 and plug it into the function. So we get 15 plus 3 sine of pi over 12 times 5. All right, and so that's just going to give me 15 plus 3 sine of 5 pi over 12. That gives me 17 point, we'll call it 17.9. Right, so, and we'll say that this is measured in feet. Okay, so the water is 17.9 feet deep. And then the question here is it rising or falling? So this was just the depth of the water at 5. To find out whether or not the water is rising or falling, we're going to have to look at the derivative at 5. All right, so let's find the derivative at t first, and then we'll plug in d prime of 5 and see what that number is. All right, so we're going to take the derivative of this function with respect to t. All right, the derivative of 15 is 0. The derivative of 3 times the function is going to be 3 times the derivative of the function. So really, the only part we really have to take the derivative of is that. All right, and it happens to be an application of the chain rule. All right, we got a sine function, and then we got a function of t inside. So the derivative of sine is cosine of pi over 12t. And then we've got to multiply that by the derivative of pi over 12t, which is just going to give me pi over 12. Okay, so if I want to know what is the change in the water level at t equals 5, then we got 3 cosine of, this will be 5 times pi over 12, just putting in 5 here, and then times pi over 12. Okay, so to evaluate that, I'm just going to do 3 cosine of 5 pi divided by 12, and then I'm going to multiply that result by pi divided by 12. Okay, and I get 0.203. Okay, so I got to think about what the units are on this. This is a rate of change in the depth of the water. It's d depth divided by dt. This is going to be the change in feet, and the time is measured in hours. So this is going to be 0.203 feet per hour. And because this is positive, that tells me that the water is rising at that point. Okay, it's raising at a point of about 203 feet per hour at 5 a.m. Okay, at different times of the day it's going to be climbing, sometimes it's going to be falling. At 5 a.m. it just happens to be rising at a rate of about 0.2. Okay, so what I'd like you to do for Monday is to work through the homework from section 3.5. It's about the trig functions. You should have written down on your sheet the derivative with respect to x of sine x is cosine of x. The derivative with respect to x of cosine of x is negative sine of x. And the derivative with respect to x of tangent x is equal to secant squared of x. Okay, so see what you can do on the homework for 3.5. I think I worked through enough examples that you should be able to do most of the stuff that's in the homework. And I'll take questions on that on Monday, and then again we'll talk about the derivative of the other three functions that you're not going to run into quite as often, but they are some things that might come up in second semester calculus. Okay, have a good weekend, and I hope this video has been helpful for you. I'll see you on Monday. Have a good weekend.